Good day, everyone. Mr. Armke back with you again for Net 125 Module 4. Today we're going to be talking about the physical layer, the actual encoding of signals into the bits that we use to transfer them across various types of network media. So we're going to look at how the physical layer functions. We're going to look at some characteristics thereof. We're going to look at some different types of cabling, specifically copper cabling, and we'll talk about UTP and STP as far as those are concerned with Ethernet networks. We're going to look at fiber optic cabling and its advantages and a couple of disadvantages, as well as wireless media, very, very common in our current networking situations. So let's get started with 4.1, the purpose of the network layer. Before any wireless communications can occur, before any physical connections can occur, before network connections can occur, we have to have a planning phase. But once that's done, we have to build upwards from that. We have to have a hierarchy. So a local physical connection has to be first. You can't have a wireless system without a backbone. You can't have network communications without a physical medium. So this connection could be wired or wireless depending on the network, but it does have to have that backbone infrastructure. A network interface card connects the device to the network and allows translation of signals coming in or going to that device. Some devices may have one network interface card. In certain cases, especially things like servers, will have multiple interfaces. Also, not all physical connections offer the same level of performance. A network interface card designed in the 90s would probably not be able to sustain the type of network connectivity we expect from even the most basic network interface cards made within the last 5 years. So the network media will come across the physical layer in the form of impulses created by the NIC to either be translated as pulses of light, pulses of electricity, or radio frequency impulses. This is the last step in the encapsulation process. Technically, it's not even part of the encapsulation process because it's more of a translation process. Encapsulation and unfolding the data into headers and eventually trailers happens more so above layer 1. So the data link layer, layer 2, is going to finalize the encapsulation process. Once the data is transmitted, the next device in the path, the next hop, if we're talking about IPv6, is going to receive that frame, basically peel off the layer 2 header in order to read it, and then re-encapsulate it, and then decides what to do with it in terms of routing or other transmission. Then we got to look at some physical layer characteristics. What are some things that automatically identify the physical layer for us? Well, usually what we're looking at are the standards that are in place from organizations such as ISO, EIA and TIA, the International Telecommunications Union, American National Standards Institute, and the IEEE. The TCP/IP standards, everything pretty much above the midsection of layer 2, because remember that layer 2 is a buffer layer. It has a logical and physical sublayer. These software standards are governed by the IETF, or Internet Engineering Task Force. We address 3 functional areas at layer 1, the physical components, the encoding, and the signaling. So the physical components, that's pretty self-explanatory. Those are the actual cables and NICs. Encoding is the process of creating a usable alphabet to be able to transmit information in a standard form that can be interpreted by multiple devices. And then signaling is the process of taking that encoded message and sending it in whatever impulses we are using. Physical components are very, very important. Obviously, we couldn't have the network without them. But otherwise, without encoding and signaling, they're just hunks of silicon and metal. So encoding means that we have to have an established primary method. In the figure here on the left, we see what's called the Manchester encoding method. And then you can also see things like 4 and 5B or 8 or 10B. In this case, we have an oscillation of voltage. If we have a voltage trough at the midpoint of the transmission, we can see here that first 0. Let me grab my laser pointer. We can see here this first 0 is basically because the peak starts up at the top, drops down to the bottom and then slides over. So that is a 0. If we come from a point of a trough and raise to a peak, or sustain that peak, then we have a 1. If we move over to that next 0, you see that it comes down and moves over. And you see that it jumps up to the top just so it can drop down again for that 4th 0. So the process means, are we looking at an S or a Z? That was what was told to me by one of my instructors when I was much younger. So if we look at a Z shape here, that would be a 0, so Z for 0, pretty easy. And then if we look at a 1, that's more of an S. And what Dr. Risnick said was S for single, Z for 0. So let me change color so it's a little bit easier to see. But you can see the S shape there and the Z shape here. Okay, so we can see that there's an S and Z kind of alternating shape, but we have to have the complete shape. If we let me switch over to blue just to indicate, look at the 2 zeros at positions 3 and 4. If we see here that we've got a Z shape, we have to start back at the top to form the Z shape again. We can't just transition across blithely. It has to be situationally aware. So that signaling method that I just showed you is how we show 1s and 0s. When we get to that midpoint of the frame, based on whatever timing or signaling we're using, that will identify a peak or a trough, top or bottom, 1 or 0. The type of signaling, of course, is going to vary based on the type of medium that you use. So if we look here, we see electrical signals over copper cable. These are going to be different based on whether or not we're using period modulation, frequency modulation, amplitude modulation, or digital encoding. So of course, if we're sending things over copper, what we expect to see in a digital form is the top left, where we can see very clear representations of what the average signal is supposed to be. If we look at the amplitude modulation, that's where we change the height of where things are going. We can see that if we look near the middle, it should be at the bottom or at the top. And we see a couple of variations in there, but in general, we kind of take these averages of the signal, and we should be able to get those representations. If we look at the frequency modulation, we see that that's the left to right, what's called longitudinal compression or decompression of a signal. You see that it's bunched very close together for a 1, spread out a bit more for a 0. If we look at the period modulation, then we see again a different pattern. Visually, for human beings, this isn't quite as instructive, but for a NIC, those oscillations, very fine oscillations of voltage, can be detected very easily. Here we see in the top right microwave signals over wireless. You can see that there's kind of these little square teeth, these little chunky teeth in the waveform, and that is because of how microwave signals are processed, the oscillation of how the signaling works. And if we look in the bottom right, we can see the light pulses. They become very strong initially, and then they decay over time. So that allows them to have separation, so they can be detected by an optical sensor at the opposite end. Now we've got a big term to discuss here. This is one you hear a lot, and it's very important to your education to understand what bandwidth means in a general sense. Bandwidth, in a very comfortable definition, is the capacity at which a medium can carry data. If we want to get slightly more technical, it is the width between the top of the frequency band and the bottom of the frequency band. So if we take the highest frequency that can be carried, subtract the lowest, then we have the width of the operational frequency of that particular band. So that's what we're talking about when the term bandwidth comes about. So how do we apply this? Well, we have to have a unit of bandwidth. And usually what we have is the bit per second, or BPS. So if we look on the left, we see 1 BPS as being the fundamental unit of bandwidth. That is one single yes or no, 1 or 0, true or false, off or on value. Can't go any smaller than that. What we can do, however, is signal so that we can send more of them in a single interval of time. So if we are sending 1,000 bits per second, or 10 to the third, we are sending 1 kilobit per second. Kilobit You know, if we use kilo, we hear those prefixes all the time. So a kilogram is 1,000 grams, things like that. Megabits per second is a million, or 10 to the 6th. Gigabit is a billion, or 10 to the 9th. And then terabit is a trillion, or 10 to the 12th. We do have naming schemes available. I believe it's exabyte that goes over terabit, or exabit, I'm sorry. That is an important little slip I just made there. The difference between a bit and a byte is a factor of 8. There are 8 bits in a byte. So when we look at gigabit versus gigabyte, we have to remember it takes 8 gigabits per second to transfer 1 gigabyte of information. So instead, if we're transferring at gigabit speed, we're actually only transmitting at 125 megabytes rather per second. 125 megabytes is equal to 1 gigabit. So because we don't worry necessarily about sending complete packets, but how many bits per second for an ISP speed, we're of course going to have to do that translation. So if we want to figure out, okay, for me to send a gigabyte of information at maximum speed, the absolute maximum would take at least 8 seconds. But because we're going to learn about throughput and how actual goodput works, we're going to see that it's usually going to take about twice the amount of time that we expect, sometimes more. Now, digital bandwidth measures the amount of data that can flow from one place to another in a given amount of time, specifically in seconds, as we've seen from the table. Now, we do have some physical laws that actually intercede to slow down how this happens. You know, we've got transmission of light in a vacuum, and we've got the possible delay based on distance, things like that. So we have to incorporate some terms to deal with what this means, you know, what these delays and accelerations are. Latency is the amount of time with delays it takes for data to move from one point to another. Usually we consider it a round trip. A data signal goes from you to the server and you get your response back. That latency time, that round trip, should tell you how long it takes to complete a single piece of the conversation. Then we multiply that by the number of conversations necessary to complete the transaction, and then we can give you an estimated time of completion. So whenever you're in your internet browser and you're downloading a file, if it takes long enough to where you can actually see a clock form and it says, you know, 7 seconds, 10 seconds, whatever else, that's what it's calculating. How fast am I downloading? What's my latency versus the size of the file? Throughput is the measure of transferred bits across the media in a given period. So bandwidth is the maximum possible. Throughput is what you're actually getting. And then goodput is the measure of usable data transferred over a given period. So the overhead, the amount of actual burden that is required to process the header information, possible lost packets, things like that, that's considered overhead. That's the burden on the infrastructure. So goodput is the throughput minus the overhead. So bandwidth is the largest possible value, throughput is what you're actually getting in bits, and then goodput is what's actually usable out of what you've been given. So you see that's a field of narrowing constraints. Goodput is what we should really be focused on, but in most cases for advertising purposes, we tend to look more so at bandwidth. So now let's take a peek at copper cabling and what it's done for me lately. Copper cabling is the most common type of cabling used in networks today. It's very inexpensive, it's easy to install, and it has extremely low resistance to electrical current flow. It's near somewhere between 0 and 5 ohms. It's very, very small. The 0 to 5 variation depends on the purity of the copper. It also depends on the thickness of the conduit. There are some limitations, though. There's some detriments. Attenuation. The longer electrical signals have to travel on a single piece of the conduit, the weaker they get. Essentially, it's kind of like throwing a baseball. If you were to throw a baseball at the speed of a major league pitcher, somewhere between 90 and 110 miles an hour, you'd be able to put a lot of force into it at the beginning, but you're fighting against air resistance, you're fighting against gravity. Momentum diminishes over time. Well, electrical impulses are no different, except for the fact there's no mass to speak of. Now, of course, we could get into the argument of mass and energy and all that stuff, but not something for this class. That's more of a physics class. The idea is, however, is the longer that signal goes on, the weaker it's going to get. Think about if you're trying to talk to somebody across, a long hallway. Now, you might get some echo, but the further away you stand, the quieter that's going to be. It's called the inverse square law. So the electrical signal, because of attenuation, means that there's a maximum distance that we can have without some kind of repeater or infrastructure device in the way in order to receive, interpret, and regenerate that signal. Now, electrical signals are also susceptible to interference from two primary sources, EMI and RFI. Electromagnetic interference is going to distort and corrupt the signal from an electromagnetic generation of like power lines. You don't want to run power lines and data lines in parallel. You want to put them perpendicular to one another. Radio frequency interference does the same thing, but that's primarily with Wi-Fi. You may get some of it with electrical signals, but it has to be fairly intense. Crosstalk can also be a problem. This is kind of a local form of interference based on if you have two data wires transmitting different information in parallel, they will interfere with each other. There's some bleed over. It's kind of like sitting too close to another table at a restaurant. You can hear everything they're saying in their conversation, and you know they can hear everything in yours. So how do we mitigate that? Well, making sure that we fix our length limits will help to keep that under control. And we can also mitigate EMI and RFI by using metallic shielding and grounding. This is the use of what's called a shielded twisted pair cable, or STP. We can also mitigate crosstalk by twisting opposing circuit wire pairs. So every pair of wires that we have inside of a standard, let's say a Cat5 cable, let's keep it real simple. We have 8 leads. They're in 4 pairs. Each of those pairs are using a transmit and receive line, a TX and an RX. What we do is we twist them together so that when they're transmitting information, we're constantly moving the information perpendicular to one another so that the information flow is not being overtly corrupted by the twist, if you will. So we're not allowing the path of those two data streams to be parallel to one another and possibly cause them to vary. If we keep twisting them perpendicular to one another, that causes their stability to increase. Again, it's just mitigation. We're not able to eliminate it completely, but we can slow it down to a very significant factor. So here we can see unshielded twisted pair. You can see the twists in it. There is a specific twist per inch ratio, kind of like how there's supposed to be 7 loops on the top of a Hostess cupcake. If we over twist or under twist, we'll start to get some crosstalk or some possible data loss. If we over twist, it's because we're shortening the cable. We're essentially putting too little transmittable conduit over a certain distance, so that tends to be potentially detrimental there. We see on the right-hand side a shielded twisted pair cable. This one is not one of the higher end ones. The higher end twisted pair cables will have a foil sheath over each pair as well as over the entire cable. You also see that there's a little plastic stem in there. That stem has 4 little branches, and it essentially helps to physically isolate the twisted pairs inside from one another. So it's reduced physical contact as well as reduced electrical contact by just using a slight layer of foil. If you look up guys like Max Faraday and try to understand how galvanic induction and all that stuff works, you'll see that a simple layer of foil does a wonderful job at trying to block close range electromagnetic signals. We can also see that in the coaxial cable at the bottom. Now I love this cross section because it gives you a really good idea physically of what's going on with this coax. We can see that there's a black polyvinyl chloride jacket on the far right hand side. That's the thick outer jacket. We can see a thinner woven braid made of usually copper. Sometimes they'll also have a copper inner jacket as well. This adds strength and flexibility while maintaining electrical isolation. We have what's called a dielectric insulator in the middle. That's that white kind of plasticky looking thing. And then the copper core conductor, the very thin copper wire in the very middle. So if you've ever seen, a standard coaxial cable that you'd use to connect a cable television or to connect a cable modem to your wall outlet, that's what the interior of that is supposed to look like. And obviously the thickness and the type of connector on the head will change based on manufacturer and implementation. So UTP is our most common networking media. It's terminated with what's called an RJ45 connector. RJ stands for registered jack, and it has 8 individual leads at the end. Now for standard network traffic, anything that's not gigabit, it only uses 4 of the 8 leads, but gigabit transmissions obviously require all 8. This is going to connect a host to an intermediary network device. So this is going to connect a host device to a switch, to a router, to a hub, that sort of thing. The key characteristics of UTP is the outer jacket, the inner plastic insulation, which is more so just for color coding, and then of course the twist in the strand itself. Now here we see shielded twisted pairs shown a little bit better detail. This one does have the individual wire pairs jacketed, as well as a jacket over the entire cable. You can see that the inner and outer jacketing is layered so that we have not only a bundle of the wires, but we also have individual wire pairs that are insulated from one another. This one does not show a plastic core in the middle, so I'm assuming that this is not a Cat 6E cable. The E traditionally indicates the core. So we can see here the coax cross section. This one's not quite as good as the actual photo, but it's the same stuff we were talking about. The three connectors that you see down at the bottom are what are called BNC, N-type, or F-type. You may also hear the BNC referred to as a B-type connector. The thing I like about B-type connectors is that you can see underneath the top of the face of the head, you can see those little notches in the side. And I like that because that actually snaps onto posts that come off the connector. That means that you don't have to thread it on with a screw. The thing I don't like about the screw threads is that while they are very snugly secured once they're attached, I find that they do tend to be difficult to get started. Getting the threads to line up can be very complicated, especially if you're connecting several devices. So I really, really like BNCs, and that's just a personal preference. If you have found a better experience with different types of connectors like this, just let me know in the comments. Now, for things like connecting wireless antennas, BNCs might not be appropriate because they're too thin. In that case, they don't really have the ability to support a locking post. You need the little threads. So an F-type would probably be a little bit more useful. The N-type is cool because it has the knurling on the outside. That cross diamond pattern gives you a little bit more grip. Otherwise, you have to use a tool like a pair of pliers or a wrench. You can also use the coax connectors for just on-site internal wiring. In certain cases, they will do those for standard coax. Just for stuff that's in the wall, and then they'll separate it out once it gets to the other side using a filter. I personally don't like that, but that's just me. Now let's get into UTP cabling. So the unshielded stuff, let's look at some properties here. Cancellation. Now whenever we have the two pairs going in opposite directions, or the two wires in the pair, excuse me, they operate on opposite polarities. Transmit and receive, one is negative, one is positive. The magnetic fields will cancel each other out as far as their exterior EMI. And then of course the twists per foot. I've heard it as twists per inch for a long time, but twists per foot I'm sure is a little bit easier to recommend because you get bigger hole numbers. Here we can see a standard Cat 3 where there's no twisting. The pairs are linked together. Cat 5, we have the standard twist, and then Cat 6, you can see down there at the bottom, has the individual foil, no, not foil, but individual plastic jacketing to help separate it. If it was foil, it would be STP. So the standards for copper cabling are established by IEEE, and the standards specifically for UTP are established by TIA-EIA, which means that the TIA-EIA 568 standard has to follow both the categories from IEEE as well as the lengths, types, and connectors that are used for the 568. So here we can see some different connectors. On the left, we can see the RJ45. There's a clear jacket, and then there's one with what's called a boot on the end of it on the right of that first image. You can see that the boot basically comes up right underneath the head and helps to prevent any potential slippage of the jacket. Here we see an RJ45 socket, what's called a keystone jack, and we can see that from the front, which is what you normally see from the outside of the panel, the strike plate. And then from the top, we can see the individual spaces where each wire would go inside, and then we'd use a punch down tool to kind of connect those. On the right, we can see a poorly terminated UTP cable. The twists are not terribly even. The jacket is too far out of the head. and there's just, it's not very clean. There's a lot of possibility that any weight or tension on that cable would cause an individual lead to start to slide out. And once you've got one sliding out and there's no tension on that other end, all the rest are sure to follow. The properly terminated UTP cable, we can see the jacket slides underneath the base of the head's little snap-in. So you can see those two little tines that are in the plastic. Those, when they're pressed down, are supposed to dig into the jacket and provide, again, some extra prevention of slippage. So here we can see the difference between the 568A and B method on the right-hand side of the screen. The first graphic, the T568A, considers the central pair, lines 4 and 5, the white, blue and white stripe, as pair 1. The orange and white stripe as pair 2, the green and white as 3, and the brown and white as 4. So in order to have a 568A cable, green is at positions 1 and 2, orange is at positions 3 and 6. Now, brown and blue don't move to 568A. What we do instead is transpose the orange and green. So 1 becomes 3, 2 becomes 6, and vice versa. So if we have 568A or B on both ends, meaning that the ends match, we have what's called a straight through or patch cable. And this is what we've traditionally used to move from a host to a network device, some kind of infrastructure device. A crossover cable, which we don't see very often anymore, this is 568A on one side and B on the other. This goes between like devices, so host to host, switch to switch, router to router. This is how you can connect two, laptops or desktops together without having to involve a switch or a hub or anything like that. Now, this is considered legacy because most NICs now use what's called Auto MDIX, Media Dependent Interface Crossover. And this is to sense what cable type is using and be able to transpose the heads, the connections inside the heads, in software. So it will logically say, oh, this is supposed to be connecting to laptops. So I'm going to automatically, instead of having pair 1 and 2 on this side read as 3 and 6 on the other, I'm going to automatically adjust it so it'll transmit correctly. So it treats it as green on both sides or orange on both sides for the patch. There's also what's called a rollover cable, which is a Cisco proprietary, usually referred to as an RS-232. You have a serial port on one side and a switch RJ45 console port on the other side. And what this does is it maps the 8 leads in the RJ45 to 8 of the 9 leads in the serial port. And what you can do then is connect to things like a console port on your router to be able to configure it. That's what we call configuring the in-band services first. Now, what I tend to use a lot is a USB to serial adapter. So it's now a USB moving to RJ45. Now, you can't use a direct USB to RJ45. You have to have that serial in between. I have seen some crossover cables, rollover cables that have been specifically configured that way, but it's important that we have a way to translate that comfortably. So just as long as you have a serial cable that works, you have the ability to access your router. You just want to make sure you have at least one. Fiber optics. This is the fun one. This is where everything's kind of been going for a while. We haven't laid new copper for networking since the mid to late 80s. So, laying new copper is older or as old as I am. So, fiber optic isn't really as common as UTP, especially because of the expense involved, but it's also a little bit overkill in certain applications. It transmits data over very long distances at incredibly high bandwidths, much better than any other networking media. Copper can't even come close to touching it. It's incredibly resistant to attenuation because light pulses, of course, light of a given intensity can reach from the sun to our planet in roughly 8 minutes. So it's an extreme amount of speed, and the amount of energy behind a single light pulse is able to carry a far greater distance. It's completely immune to EMI and RFI. There's no electromagnetic interference because the frequencies of a light pulse are way, way different than a standard radio frequency transmission. So fiber optic cabling is made of very flexible, extremely thin strands of very pure glass. So this has to be glass that is free of any kind of impurities, because anything that's in the glass will diffract the optical transmission. So we have to make sure that this glass is very, very clean, chemically speaking. We use a laser or an LED to encode bits as pulses of light, and we'll see the difference between those two when we get to single and multi-mode in just a moment. The fiber is going to act as a waveguide, transmitting light between the two ends with minimal signal loss. So very much the same as a periscope on a submarine. Essentially, you can build this, you can test this in your home with a pair of small mirrors and a cardboard tube. Essentially, you angle the two mirrors parallel to one another with their reflective sides facing inwards, and you can kind of look around a corner at that point, because the light waves of the two mirrors bouncing off of one another passes it to your eyes, even though you're not directly in line with the line of vision. And you can do this over several distances. Unfortunately, after numbers of bounces, if you will, the number of refractions or diffractions, the light energy does start to diffuse quite a bit. You get what's called fuzz out from the lack of light intensity. But it will work. So a single mode fiber that we see on the left is going to give us a very small core, uses very expensive lasers to make sure there's a very precise single path for light, and it's good for long distance applications. So we see here the glass core is 9 microns thick. If you want to look up what a micron is, it's very, very thin. The cladding, the glass that goes around the core that's not for transmission purposes, is 125 microns in diameter. This is usually glass that has been treated so that anything that is bouncing or diffusing based on bend radius or things like that will angle back in towards the transmission. So the glass that's on the exterior cladding is usually opaque, very, very close to solid. There's something in there that's a mixture that optically will not absorb the light. And then we have a polymer coating on the outside for the jacket. On the right-hand side, we see a multi-mode fiber. This is a larger core. It's able to use LEDs to generate several different light paths. The core in that case has to be thicker, somewhere between 50 and 62.5 microns, depending on the version. The cladding is the same thickness, but because it's spread out over a larger core, the cable becomes thicker, and then you have your coating. Now, this is able to run up to 10 gigabits per second over 550 meters. So 550 meters, if you want to do the math, it's 3.3 feet per meter. So, if we say it's roughly 3 times that length, that's somewhere around 1,800 feet. Or 1725, excuse me. So dispersion is the process of light in a wave pulse spreading out over time. We can see here dispersion or diffusion of light through a prism in the graphic here. And what happens is different wavelengths of light that make up white light are separated out based on their frequency. So the slower frequencies of the red light you see phasing out towards the top, and then the higher frequencies, the shorter wavelengths of blue and violet light coming out towards the bottom. So the white light we see is all kind of bundled together, but as we filter it and separate it, we see that there's a difference in how that transmission occurs. The more dispersion we see, the more signal strength loss we see. Now, multi-mode fiber is more susceptible because of the thicker core. If we have a well-collimated stream of laser energy and we have a very thin channel in which to operate, as single mode does, there's not as much opportunity for dispersion. Now, fiber optics tend to be used in a couple of different types of industries. The 4 big ones are enterprise networks, which backbones the cabling between local, like between different WANs. WAN-to-WAN connection would usually be fiber. You can also interconnect infrastructure devices with short fiber optic cables in order to ensure quick connectivity between routers, which are usually going to have some distance between them. Fiber to the home, or FTTH, sometimes called FTH. I don't know why they abbreviate just the one T. But it's used to provide bandwidth services to homes and small businesses, so things like Google Fiber, AT&T Gigapower, which uses fiber connectivity, that sort of thing. Long-haul networks, these are connections between countries and cities and things like that. These are the big backbone cables that go between ISPs of different levels. If you take CTI 120 with me, you'll hear about tier 1, 2, and 3 ISPs. Submarine cable networks, these provide high-speed, high-capacity solutions capable of surviving in harsh undersea environments at up to transoceanic distances. I'm trying to remember if I talked about this when I recorded the original version of this video, but there is a cable that goes from Bilbao, Spain to Virginia Beach, Virginia. It's about, I want to say it's like 15 or 1600 meters, or 15 or 1600 miles long. It's a super long cable. It's only the size of a garden hose. It has 8 internal cores, single mode to be able to transmit over those nice long distances without any kind of impediment. And it is owned by Facebook and by Microsoft, and it runs about 10 terabits per second. So about 1.25 terabytes of information per second can be translated. Pretty massive. Now, our focus in this course is going to be the use of fiber within enterprise environments, but if you're curious about the other stuff, it's the same principles, it's just implementation. So you can do a quick Google search on that if you wish. Here we see a couple of different fiber optic connectors. The ones on the left are what we call straight tips. You can see that the ferrules, basically the ends of the connector cables, the light recipients and transmitters, stick out of the ends. Subscriber connectors tend to sheathe a little bit more of the ferrule there, much longer boot on the head. We can see a Lucent style connector here, a little bit more squared off. This is going to have a little bit easier time being able to snap into a connector and remain stable. You can see that the head of the jacket head is pretty long, snaps in pretty deep. Same thing with the duplex multi-mode LCs. Now the reason that one is called simplex and one is called duplex is because to be able to transmit in duplex, you have to have 2 different fiber optic cables, one for your upstream, one for your downstream. So you can use 2 LC simplexes or 1 multi-mode LC duplex. So here we can see a Lucent, what's called an SM patch cord, single mode patch cord. And you can see a straight tip to an SC on the right. These patch cords are in yellow. There is a little bit of color encoding we traditionally talk about. We can see the orange here for the 2 single connectors. This is multi-mode. Notice that it's orange. And then the straight tip to Lucent multi-mode patch cord. So whenever we see yellow, of course, you will think of single mode, whereas with the excuse me, with the orange, you will think of multi-mode. And I believe aqua is also a multi-mode type that can be used. Now, optical fiber is primarily used as backbone cabling because it's high traffic and it's point-to-point. That makes the return on investment much better. There are also sometimes connections between data distribution facilities, building interconnections, and multi-building campuses. So if we're talking about, for Cape Fear's North Campus, we've got the NA building, NB, the cosmetology building, early high school, all that stuff. If they were further apart, or if we needed that really high speed transition, we would have optical fiber going between them. I haven't done the investigation of whether or not we do. I would assume we do just because of how new the building is. Now on the right hand side we see a table here comparing essentially UTP to fiber optic. The bandwidth supported twisted pair goes up to 10 gigabits. Fiber optic can do about 10 times that. 100 meters of distance can be covered. 100,000 meters or 100 kilometers can be covered with fiber optic cabling. Almost completely immune to any kind of electrical hazard or EMI or RFI because it's not an electrical impulse versus UTP, which is it's low, but it's still there. The cost, of course, is going to be the lowest on UTP and highest on fiber optic. And that means the cost not only for installing, but securing as well as the physical product. Now let's talk about wireless frequency. This is one you'll see quite a bit. Wireless frequency transmission deals with electromagnetic signals representing binary digits with a high or low tone, essentially. That's the greatest mobility option possible. It allows us to connect in buildings where we couldn't necessarily rerun infrastructure. Let's say that we had a historic building and we weren't allowed to do anything to the, the drywall or the lath, the, supporting infrastructure. So we would have to, in order to support any kind of network transmission technologies, have all of our hardwired connections, all of our physical connections, exterior to the building or somewhere that it's not being, tacked down. At that point, we could then use a wireless hotspot or an access point with enough range to cover what we need. So the coverage area of a wireless transmission type is usually impacted by the physical characteristics of where it's deployed. Like if you have a building with a certain type of metal roof, you probably have really bad cell service. If you are in an area where maybe you have a lot of overhead power lines or things like that, that will cause problems. Certain types of large electric motors, hospitals with a lot of electronic equipment, there's going to be a lot of interference. Security. So this is difficult because we want to have confidence in wireless transmission, but what we're doing when we're creating a wireless transmission is sending a radio frequency out kind of into the air, and we hope that it gets picked up and concentrated, by an access point that is able to interpret and process it correctly. And then we're able to transmit between our AP and our local host device and be able to carry out our business. The way that we secure it is by encrypting the packet, but no matter how well encrypted something is, if somebody has enough time or accessibility, they could theoretically crack it. So we have to be careful with wireless technology. We have to make sure that we're aware that there is an intrinsic security leak just by using wireless. It is also a shared medium. So we have half duplex transmission that goes on, meaning that we have a send mode and a receive mode, and it alternates between them. If we have a number of users accessing the wireless LAN simultaneously, that means that those individual upload-download lines start getting bogged down. So that means that the bandwidth transmission will start to reduce after a certain saturation point, meaning that once we have a certain number of users, we will start seeing deleterious performance. It will start to go down. Now, the industry standards for wireless communications from IEEE, ITU, all that stuff, cover OSI layers 2 and 3. In each standard, we talk about physical layer specifications that dictate the data to radio signal encoding methods, the frequency and power of the transmission, so how strong can that signal actually be, what's the reception and decoding requirements, how are the antennas built. There are 4 different major wireless standards we talk about. Wi-Fi, which is 802.11, Bluetooth, which is a personal area or Piconet, 802.15, WiMAX, which uses microwave technologies, 802.16. That's what's called a point-to-multipoint. Essentially, we treat it almost like a cellular signal. And then we have what's called Zigbee. This is 802.15.4, so this is a subset of the same standards we use for Bluetooth. Low data rate, low power consumption. It's meant to send predominantly just control signals for Internet of Things devices. So if you're sending a control signal to turn your thermostat up or down to your Nest thermostat from your phone, Zigbee would be a really good idea because it's not going to consume a lot of power, it's not going to consume a lot of data. It's just going to take those standardized signals and use a very specific subset of those frequencies to be able to transmit. In general, a wireless LAN requires 2 primary devices: wireless access point and the wireless NIC. So that means that your backbone, your receiving devices, have to have a wireless access point. That's the end point of the physical network. Now it's transmitting wirelessly to be able to send and receive. And then your device, your host device, has to be able to have a wireless NIC to generate the signals necessary to provide capability for wireless communication. There are several WLAN standards, which we just talked about. So when you're purchasing your equipment, make sure you've done your planning and that you have the ability to ensure compatibility and interoperability. Administrators also have to develop and apply very stringent security policies to protect WLANs from unauthorized access and damage. We have to make sure that the wireless frequency isn't going too far out of the physical range of the buildings so that somebody couldn't camp just outside of sight maybe and try and hack in or try and intercept traffic. That is chapter 4.7. So we can, of course, go back over whatever we need to in class if you wish. If you want to go back over the notes here, or if you want to look at the individual chapter breakdowns on the NetAcad website, you can certainly do so. If you have any questions or concerns beyond that, of course, you can always email me at jearmke063@cfcc.edu. If you have any concerns beyond that, or if you need something a little bit more immediate, you can always contact me by text or by phone call at my Google Voice number, which is 910-239-7814. Thank you so much for your time and attention. Hope you have a wonderful day, and I will see you next class.